who will present work on learning synthetic environments for reinforcement learning. So in this case, we are not adversarial to agent against each other, but we have we evolve environments that are increasingly hard for agents to solve. Go ahead, Fabio. You can unmute.
Yeah, thank you. Thanks, Joaquin, and thank you very much for the invitation, and thanks to the organizers for organizing this great workshop. My name is Fabio, and this talk will be on learning synthetic environments for reinforcement learning with evolution strategies. And this work was in close collaboration with Thomas Nierhoff and Frank Hutter, and you can follow us on Twitter. Okay, I'd like to say a few words about the people on this project. First off, Thomas Nierhoff, who is first co-author and who I was lucky to have as a master's student and who did his master's thesis on this work. And he is responsible for major parts of this work, including designing and maintaining the code base, spending countless days testing new ideas and model variants. And Frank Hutter, who I'm extremely lucky to have as a supervisor, and who I'm thankful for allowing me to explore new and risky ideas with his unlimited support. So in practice, training reinforcement learning agents still remains cumbersome and challenging. In the best case, it is often time consuming, but it's also sensitive to hyperparameters and initialization, such as seeds and weights. And in the sparse reward setting, the explorative capabilities of agents become quite important. You also have to deal with delayed rewards. In the dense reward setting, you basically ask a human designer to model a task, and to him or her, it is often unclear how to do that, and heuristics are not necessarily helpful for agent training. And in the real world setting, you often have problems like human safety and robotics, where robot manipulation can be dangerous, where, for example, the manipulator explores this space with high velocity motions. And there are many more problems. And a natural question arises, at least to me, is can we also tweak the environment or the task or the data set instead of the agent or the learner? And turns out, yes, in fact, there exists a multifaceted work. For example, these are just a subset of what one can find. Some basically are concerned with distilling data sets. Some do reward shaping instead of learning states and rewards. Some do this in an agent agnostic fashion. Some do it with gradients. Some do it with evolution. And but most, if not all of these works sort of address in some way or another the following general question. Can we learn a proxy data generating process that allows to train learners more effectively and or efficiently compared to when trained directly on the original data generating process? And the learner here can be, as a general term, can be anything like a learning machine and machine learning. In supervised learning, that can be a classifier, a segmentation. In reinforcement learning, that's typically an agent. And benefits next to efficiency and effectivity, for example, can be cheap to run proxy environments and data sets that basically allow fast evaluation. In AutoML, for example, we can, once we have something like this proxy data generating process, we can gain insights about the underrepresented classes that might be there, the importance of certain states or trajectories. But before working on this project on learning environments, we were very much inspired by this great work called generative teaching networks, also mentioned before during the last talk. And so I think didactically, it does make sense to develop our idea based on GTN. And as mentioned earlier, the main focus of this paper or of GTN is to generate a small synthetic data set that trains a neural network classifier on MNIST or CIFAR within a few batches to high accuracy. And this is done in this paper through a bi-level optimization. And in the inner loop, you have a neural network generator, which is fed with random noise, and it outputs synthetic data samples. And the learner is trained on these synthetic data samples and learns with or trained with standard SGD. And in the outer loop here in yellow, the synthetically pre-trained learner is now switched and moved over to perform on the real data and basically evaluated there. and the loss is used to compute a meta gradient to update the generator, basically backpropping through the entire inner loop. And results can be seen here. This is just an example taken from the paper. And yeah, through the aid of the learner, the generator learns slowly to generate samples so that fast training is achieved. And this is also related to dataset distillation. And yeah, we adopted this idea and applied it to reinforcement learning. And we switched off the generator and called them synthetic environments, short SEs. They're still neural networks. And we switched off the learner by reinforcement learning agents. And then the real data becomes a real environment or a task such as OpenAI Gym, Carpol, or Acrobat, which we used here in this in our work, but could be also a Mujoko task or yeah. And for computing the meta updates, we use natural evolution strategies instead of second order meta gradients. And of course, this turns the synthetic environments into a population of the synthetic environments. And we got rid of the noise. And yeah, as in standard RL, the synthetic environment has the same API. Essentially, the agent acts in the synthetic environment and gets the next state and the reward. And algorithmically, that looks like this. So we start off with a random initialization of the synthetic environment parameters, denoted as psi. We have a real environment, capital epsilon, and a perturbation vector distribution, small epsilon, which is a multivariate Gaussian with zero mean. And then we have two parameters or hyperparameters, number of episodes n sub e, and the population size n sub p. And then in the inner loop, each population member is basically perturbed by the SE parameters, perturbs the SE parameters with a sampled perturbed vector, the small epsilon. And now we use the perturbed SE to train an arbitrary freshly initialized agent for n sub e episodes. And you can think of, we'll go into the details later, but the agent here we used throughout was DDQN, because we have a discrete action space, typically in Carpol and Acrobat. And n sub e, we used maximally 1000 episodes. And we run the depicted algorithm in parallel, meaning that each population member is run concurrently. What we do then, in the next step, is we freeze the agent parameters and evaluate it on the real environment. We do this always across 10 test episodes, and this yields the average cumulative reward, which we use as a score for each population member. And then we update the SE parameters through a weighted sum over all population members. So we weight the member scores by the perturbations, also called the score function estimator. And we repeat this n sub o times and early stop when the resulting SE is capable of training agents such that they can consistently solve the target task. In Salamans et al. Work, evolution strategies as a scalable alternative to reinforcement learning, I just want to briefly point this out. They also use ES to evolve a population, but here they use agent parameters. So they evolve agent parameters. Here we use ES to evolve the SE parameters. And also we want to point out that we have a meta learning problem here. So meaning we have two optimizations going on. We first optimize the agent and over the outer loop, we optimize the SE parameters. And how do we run the proposed algorithm? There are quite a few hyperparameters to be set. This is a subset. So we have agent hyperparameters and NES hyperparameters. What we did was we used Bob to optimize the hyperparameters for Carpol and Acrobat separately. And we used 20 Bob workers, each process one population of 16 members. What we did not optimize, because these hyperparameters could potentially negatively affect the HPO runtime, was the population size, the number of train and test episodes. And out of this HPO came that we should use mirrored sampling, similar to Salamans et al. Work. A score transformation, also similar, but slightly different. And yeah, since this added an expensive second outer loop, essentially to do HPO around this meta learning algorithm, we did this only the beginning of each task. So first for Carpol, later on for Acrobat, but only in the beginning. As soon as we had the hyperparameters, we stopped using that second outer loop. Yeah, of course, before running this algorithm, we need to address a few more details. For example, how long do we train the agent on an SE? The problem here is that the rewards that we get from the SE may actually not be informative about the current agent performance on the actual task. So they might not say something about the actual task performance. And this is where our heuristics come in. So for, heuristics for early stopping the train agent function and the algorithm. So we maintain two non-overlapping moving averages of the train rewards, namely the last 10 and the last 20 episodes, and then we early stop as soon as the absolute difference between both is smaller than a threshold. Since we're also training on agents for the baseline, we want to briefly mention the heuristic here. We stop training agents here when the reward exceeds a certain solved reward threshold for the last 10 episodes, and that is defined by the task. In carpool, that's 195, for Acrobot, that's -100. And in case no heuristic is triggered, because, for example, the policy is just not really converging, we train for 1,000 episodes at most. Evaluation is much simpler. We always, in this work, evaluate on the real environment, as I said, for 10 test episodes. And this gives us the cumulative rewards, which we collect for the upcoming visualizations. So this was a lot of information to take in. This is why I have this TLDR table. So in column-wise, we have the events, basically, train the agent on the real environment, train the agent on the synthetic environment, if no heuristic is triggered, and evaluate agent. And you can see here that when we train the agent on the real environment, we simply use the solved reward threshold. On the synthetic environment, we look at, has the performance converged with respect to the rewards? And if no heuristic is triggered, we train for at most 1,000 episodes. And evaluation is always done on 10 test episodes. So let's look at our results. After identifying stable hyperparameters, we ran the depicted algorithm with the defined heuristics and DDQN. At the top, you can see carpool in blue, and at the bottom, you can see Acrobot in orange. And each thin line are the rewards or the scores of the evaluate agent function, basically across the values across the 16 workers as a function of the ES outer loop. And the thick line is simply the average of the thin lines. And you can see some sort of variance also going on. We think this is because of the stochasticity of natural gradients and because of the sensitivity of reinforcement learning agents to seeds and initialization. And with the given results, we basically show that it is possible to identify SEs that are able to train the agents such that they solve carpool and Acrobot. And this, as you can see here, it is often sufficient to do this only for 50 outer loop steps. Then we can also already solve these two tasks. And we want to briefly mention that we found that randomly sampling the agent hyperparameters in the inner loop actually leads to better performance. And so we, with hyperparameters, I mean we vary the learning rate, the batch size, the hidden layers size, and the number of hidden layers. And unless denoted otherwise, we follow this protocol. So for now, we have shown that SE trained agents can solve tasks, but how effective and efficient are they actually? And to showcase this, we conducted some additional experiments. So we learned a bunch of synthetic environments and chose 40 different capable of solving the task. And on each of the 40 SEs, we trained 10 DDQN agents with and varied their hyperparameters. Again, learning rate, batch size, hidden layer size, and number of hidden layers. And after training, we evaluated each agent on the target task across 10 test episodes, and we used the cumulative rewards again of these 4,000 evaluations, really. So 40 times 10 times 10, 4,000 evaluations for plotting the upcoming visualizations. So for this experiment, this is all on carpool for now. We used the visualization through violin plots. We executed basically the same procedure as I showed in this diagram for a real environment as a baseline, just so that we can compare actually if training on SEs is actually beneficial over simply training on the real environment. And at the top in this visualizations, you can see the average cumulative reward over these 4,000 evaluations. And at the bottom, we can see additional statistics such as how long did the training go, how many episodes did we need. And in orange now, in this violin, you can see the results when the DDQN agents are trained on SEs. And below, how many steps were required until the heuristics for stopping the training agent were triggered. So you can see that it is generally shorter, but the performance is still good. The heuristics trigger early, and we require 60% fewer training steps compared to the baseline. We also want to mention that despite actually triggering early, yeah, we actually outperform the baseline here in terms of requiring fewer steps. And it's also more robust because the standard deviation seems to be lower here. It seems that the SEs have learned a very efficient informed representation of the target task that they can show to the agents and prepare them for the actual task. And finally, on the right side in green, we can see that we show the results when we don't vary the hyperparameters during SE training. And as mentioned earlier, the performance is worse, probably due to overfitting. So if you don't vary the hyperparameters during SE training and just use default hyperparameters, it seems to be overfitting to these hyperparameters. Of course, it is difficult to justify the argument of speed improvement when a lot of environment observations have gone into training an SE, and therefore it would be nice if these SEs would be able to transfer to other agents and be able to train them as well. And that's why here we chose dueling DDQN. So the SE was trained on DDQN, and now we transfer to dueling DDQN, and we use the same models as before. And we point out, that we use the same hyperparameter configuration space as before also. And here we still achieve 50% fewer steps on average, and it's also more stable. And then another question is, can we actually transfer from Q-learning DDQN, dueling DDQN, where Q-learning agents to actor-critic agents as well? And here we show a transfer to TD3. Of course, carpal is a discrete action space task, so applying standard TD3 is not possible. That's why we adapted TD3 to handle discrete action spaces by using a Gumbel softmax distribution. And we can see that the transfer here does not work as well, possibly because actor critics employ a very different learning dynamics than the Q-learning methods. But as a side remark, when running these experiments, we also saw some consistency. So bad SE models tended to be bad and good ones tended to be good. And also we can see that from the low standard deviation, if an agent actually, if the training succeeds, it remains quite efficient. But this is something we need to investigate further in the future. And we also have some plots for Acrobot. We did the same thing for Acrobot, and here we have a speed up of 38% faster training. And so in the end, one might ask, where does this efficacy actually stem from? Why are they so efficient? As we pointed out, this might be due to an informative representation. And we tried to analyze this, and we took advantage of the small state space of our tasks and conducted a qualitative experiment to understand this behavior better. The procedure was as following. So we randomly selected an SE. We trained 10 DDQN agents on it, and we collected the states, actions, rewards, and next states, so these tuples. And then we evaluated these SE trained agents on the real environment and again collected the same tuples. And then we visualized these collected next states and rewards as histograms. And the colors here indicate the origin of the data. So we can see that some, so in orange, you can see the real environment tuples shown, and synthetic environment is in blue. And we can see that some synthetic data state distributions are shifted and narrower, for example, the car position. Potentially, we believe because the SEs are biasing the agents towards helpful and relevant states for learning. And the synthetic reward distribution down here is actually wider, indicating that the sparse reward distribution became a dense one, basically doing something like reward shaping. And in green, what we depict here in green is the SE responses when we feed it with real environment data. So here we try to answer the question, does this shift of distributions actually come from the SE or from the agent? And to analyze this, we actually looked at the SE responses and fed it back into the real environment. And the distribution still align better with the SE than with the real environment, indicating that the shift is more caused by the SE than probably more caused by the SE than by the agent. So to conclude, it seems possible to train SEs, which act as effective proxies for reinforcement learning target tasks. Here only shown for Carpal and Acrobat, but we believe that's a start. And empirically, we have basically seen significant training speed ups and stability, despite varying hyperparameters. Of course, you could vary additional hyperparameters, but we believe that's also a start. And we have shown early signs of transferability, making this an interesting and valuable method for the future. For future work, we actually want to look at more complex environments. Also there, we would have more algorithms to show the transfer possibilities. And we also want to understand the trade-off between the target task complexity and the resources that we actually need. Keep in mind, we only used a population size of 16, and we'd like to scale that up a bit and see how far we can go in terms of environment complexity. So code and models are available under this link, and thanks a lot. And I'd be happy to take questions now.
Thank you very much.